Okay, 7.2 is on the calculus of parametric curves. Okay, so we have the calculus of parametric curves. So let's cover differentiation. Okay, so suppose f and g are differentiable functions. And we want to find the slope of the tangent line at a point on the parametric curve x equals f of t and y equals g of t. That is, we want to find dy dx given y is differentiable at x, okay, then dy dx is equal to dy dt over dx dt if dx dt is not equal to 0. Okay. So we take the derivative with respect to t for y, and then take the derivative with respect to t for x, and then divide the two, and we get the derivative of y with respect to x. Okay, so let's do an example with this. Okay. Actually, before we do an example, let's see where this comes from. Okay, if we look at dy dt, okay, we could think of this as dy dx times dx dt. Okay, this is by the chain rule. Okay, think of as this dy dt, okay, g prime of t, okay, is equal to dy dx. Okay, so if we think of this as y is equal to g of t, and x is equal to f of t, okay, then what we get is we get dy dt is equal to g prime of t. The x dt is equal to f prime of t. But what would dy dx represent? Well, dy dx would be, the derivative of y with respect to x. You'd have to have a nested function in order to do that. You would have to say that what is y in terms of x? You'd have to be like, well, y in terms of x would be f of g of t, right? This is y of x. Okay, And if you wanted to get what y prime was, y prime in terms of x, y prime of x, which is dy dx, you would have to take the chain rule here. You'd have to say this is f prime of g of t times g prime of t. I think I did that backwards, actually. Is that right? Because it should be y of, yeah, this is backwards. I'm sorry. Okay, this should be g of f of t. My bad. Okay, because it's y of x. Y is g of t, and x is f of t. Okay, so we get g prime of f of t times f prime of t. Okay, and so okay, so dy dx is equal to, or sorry, dy dt. How do I want to do this? So that's dy dx, yes. Okay, that makes sense. Does it though? Let's not do dy dx there. Let's just use this. G prime of f of t, that's going to be dy dx. Okay. Because this is going to be y of t now. No, that doesn't make sense. Derivative of, okay, that's y prime, that makes sense. Okay, and this is the chain rule, yes. Okay, so why am I getting dy dx and t? So this is dx dt, but now they're saying that this is dy dx. Okay. So y is g of t, dy dt is g prime of t. Okay, that makes sense. Because we're putting everything in terms of t. So then, I see what I need to do here. This is y of x of t. Okay. So we have to think of it in terms of y of x of t, which is really y of t. Okay, which is really y of t is equal to g. So when we take the derivative of that, that's going to be y prime of t. Yes, okay, there we go. That makes more sense. G prime of f of t times, yeah. So this is going to be dy dx, and this is going to be dy dt. Okay, so I'm going to go dy dt is equal to dy dx times dx dt, and then I'm going to divide dx dt, dx dt. We get dy dt, oh, sorry, dy dx is equal to dy dt over dx dt. Okay, if dx dt is not zero. So x can't be a constant. Okay, in order to do this method, we cannot have x be a constant. It has to be some function of t. Okay, so let's do an example with this. A curve is defined by x equals t squared and y equals t cubed minus 3t. Find the equation of the tangent line when t equals 5. Okay. So we want x equals t squared and y equals t cubed minus 3t. So I want dx dt equal to 2t and dy dt to be equal to 3t squared minus 3. So what is dy dx then? Dy dx, okay, is going to be equal to dy dt over dx dt. So that's going to be 3t squared minus 3 all over 2t. Okay, that's going to be in the slope of my tangent line. That's going to be m. Okay, so the slope of my tangent line, m, is 3t squared minus 3 over 2t. So all I have to do is figure out what I need a point and I need the slope when t is equal to 5. Okay, so what is x when t is equal to 5? Well, it's 5 squared. Okay, I'll go when t equals 5, x is equal to 5 squared, which is 25. So x equals 25. Okay, I'm going to call that x1. Okay, y1 is equal to t cubed minus 3t, t cubed minus 3t. So that's 5 cubed minus 3 times 5. So that's 125 minus 15. So y1 is equal to 110. Okay. Okay, and then what's m? What's my slope when t is equal to 5? That's going to be 3 times 5 squared minus 3 over 2 times 5. That's 3 times 25 minus 3. Okay, that's 72 over 10, which reduces to 36 over 5. Okay. So we have a point, 25, 110, and we have the slope, 36 over 5. So I'm going to plug this into point slope form. Y minus y1 equals m times x minus x1. We can find the equation of the tangent line. Okay. So y minus 110 is equal to 36 over 5 times x minus 70, or sorry, x minus 110, or sorry, 25. Okay, so let's distribute. This becomes y minus 110 is equal to, okay, 36 over 5x, and then this is going to be minus whatever 36 times 5 is. So that's going to be 180. Okay, I'm going to add the 110. Then I get y is equal to 36 over 5x minus 70. Okay, and that's the equation of my tangent line. Okay, I can write it in as this, or I can put it in parametric form. Okay, we call this rectangular form. Okay, or I could say, well, let x equal t. And so y is equal to 36 fifths t minus 70. We could do that. If you don't like the fraction, you could, multiply everything through by by 5, and then you could say, well, you know, you could parameterize this however you want, you know, but you could parameterize it differently if you if we wanted to get if we want to put this in standard form, we could do that too. We could say that this is 5y is equal to 36x minus 70, right? And then 36x minus 70. We could, there's a way to write this so that, let's think. So so that it's not a fraction. No, I don't think so. I think you're either going to have it as a fraction, or I don't think we're going to be able to get rid of the fractions. Because because we have it in terms of x and y. Because we could, if we put this in standard form, this would be 36x minus 5y is equal to 70. Okay. Yeah, I'd have to still use fractions in order to parameterize this. If I let, say, t is equal to x over 35 or x over 36. Okay, for t over 36, yeah, it's not going to work. So just don't worry about it. Okay, so let's just parameterize it like this. If we, what could we do here? Oh, you know what? There is kind of a way to get rid of the fractions if we wanted to. I think. What if we, so this would be parametric form. What if we let x equal 5t instead of just t, right? Then what happens when we let x equal 5t? We plug it in here, and we get y equals 36 over 5 times 5t minus 70, and the 5's cancel out. And we're just left with y equals 36t minus 70. So that's another way to parameterize it, so that you don't have to deal with the fractions. So we were able to do that. Okay, I thought that we might be able to. X equals 5t, y equals 36t minus 70. That's another parametric form that doesn't involve fractions. Okay, let's talk about integration for a second. Okay, let f and g be functions defining a parametric curve x equals f of t and y equals g of t. The area under the parametric curve for alpha is less than or equal to t is less than or equal to beta is as follows. Okay, a is equal to a to b of f of x dx, which is equal to a to b of y dx. Okay. Okay. Okay, but we need to think of this as y of x. Okay, so this is a to b of y of x dx. So if we change the parameter here, if we change the parameter to t, we're going to get different limits of integration, and this is going to be g of f of t, okay, g of f of t, which is really just g of t, okay. I can just rewrite that as, but what's dx? What's dx dt? We have to turn this, so this is y equals g of t. I don't like the y of x. Let's just leave it as a y. Okay, so let me just, yeah, leave it like this. So this is y, which is g of t, times from alpha to beta. Okay, y ends up being g of t. Okay, that's good. But what's dx? Let's change dx into something that involves t. Okay, so what is the derivative of x with respect to t? Okay, well, it is equal to f prime of t dt, or f prime of t. So, or we could think of it the other way. F prime of t, let's think of it this way. F prime of t is dx dt. And so if we multiply both sides by dt, we get f prime of t dt is equal to dx, which is what we want. We want dx in terms of dt. So this is times f prime of t dt. Okay, and this is our parametrized formula for finding the area under a curve. Okay, this is the area under a parametric curve. Okay, number 2. Find the equation for the area of a circle. Okay, if x is equal to r cosine t, and y is equal to r sine t. Okay, so this is a circle centered at the origin. Okay, but has radius r. Okay, centered at the origin and has radius r. Okay, so let's find the area. Okay, so this goes from 0 to 2 pi. A is equal to 0 to 2 pi of g of t. Okay, so what's g of t? That's y. Okay, y is g of t. So g of t is equal to r sine t. That's r sine t. And then what's f prime of t? Well, that's the derivative. That's dx dt. That's, well, what is dx dt? Dx dt is going to be negative r sine t. Okay, so we're going to plug this in negative r sine t. Okay, dt, let the dx be the dt. Dx dt is equal to r, so okay. Then we've got the dt here, f prime of t dt. Okay. Okay, so let's take a look at this. This is a is equal to uh, let's pull out a negative r squared. Okay, and then we've got 0 to 2 pi of sine squared t dt. Okay. So now let's do our half angle identity. This is 1/2 minus 1/2 cosine 2t. Okay, from 0 to 2 pi of negative r squared. Okay. So then we could do a u sub on this. U is equal to 2t. Du is equal to 2 dt. And so divide by 2. Okay, and so this becomes, and also we need to change our limits of integration. This is now going to go, u of 0 is going to be 0, but u of 2, I'm sorry, u of 2 pi is now going to be 4 pi. Okay, so 0 to 4 pi, negative r squared times 1/2 okay, minus, okay, 1/2 cosine u times du over 2. Okay, cool. What I'm going to do is I'm going to factor out a 1/4. Okay, let's see what we get here. So, okay, so let me factor out a 1/2 first, and then I'll factor out the 1/2, the 1/4. So 0 to 4 pi. This is 1/2 times 1 minus cosine u times d over 2. That's really 1/4 du. Okay. And so this is going to be negative r squared over 4 times 0 to, okay, 4 pi. And so we get 1 minus cosine u du. Okay, so this is going to be u minus sine u from 0 to 4 pi. Okay. So let's see what we get here. We get 4 pi minus the sine of 4 pi minus 0 minus the sine of 0. Okay, so the sine of 4 pi, that goes to 0. This goes to 0, and that goes to 0. Okay, and we get just 4 pi. So this is negative r squared over 4 times 4 pi. 4's cancel out. I get negative r squared pi. Okay, or negative pi r squared. The only problem is this negative. Okay, so we want to kind of reconcile the negative here. Okay, so if we think about what's happening here for this circle, okay, let's think about what's happening. Okay, we're starting off with, when t is 0, we would get r, 0 and r. Sorry, we would get r and 0, right? We'd start here, okay, when t is 0. Okay, and then we would go all the way around. Okay, and we would want to get some area here. Okay, the problem is that we're getting positive area and we're getting negative area. Okay, as we go around the circle. Okay, and those areas are kind of messing with each other. So if I could just use the symmetry here and leave it to go just partially around the circle, okay, or if I could get rid of the negative altogether by changing the way I parametrize the circle, okay, and where did the negative come from? The negative came from this here, okay, from r sine t. So if we can parametrize the circle however we want. We don't have to start at t equals 0, being at this point. We could actually start t equaling 0 at this point here. This is my new t equals 0. Okay. And in order for t to be 0 there, I would have to let x be sine and y be cosine. So if we move, okay, t equals 0 from here to here, then x equals r sine t and y equals r cosine t. Okay. So if we do this over again with that idea, okay, and we switch these, okay, I'm going to kind of just rewrite some of the things that we got. Okay, so if we do r sine t and r cosine t, okay, then what do we end up with for dx dt? Well, we keep things positive. It's r cosine t now, and r Okay, g of t is r cosine t. So instead of it being sines, I end up with cosines and things are positive. So this becomes r cosine t times r cosine t dt. That allows things to be positive. Instead of sine squared, I get cosine squared t, but that's fine because I can just change this to a double angle with just a positive result. This gives me positive, 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 and it will eventually eliminate the negative all the way down. Okay, and so that gives me the area of my circle pi r squared, which is what we should know on anyway. Okay, so we had to reparametrize in order to get rid of that negative sign. Okay, instead of starting the circle at x being cosine, I started the circle at x being sine, but I still went from this point at t, then my new t equals 0, I still went all the way around the circle. I just chose a different starting point so that I could make things positive when I took the derivative of x. Okay, but all the math still works out. It's just allows me to write it as a positive area instead of a negative area. Okay, and that is section 7.2.